As mentioned in the previous video, there are a couple of practical problems with the really simple circuit we looked at for a slew limiter. And one of these is that we would rather have a little bit better control over the output impedance. The output impedance of that output op amp is very close to zero. We're probably going to want to increase that output impedance to prevent problems when we connect this to other circuits. So we're just going to add a resistor at the output. The other problem is that if we try to drive that RC circuit directly with the input buffer, if we set the variable resistor to zero, then when the input voltage changes, all of a sudden we have some voltage on the capacitor, we have some different voltage coming out of the input buffer, and there's no resistance between. If the variable resistor is set to zero, that would imply infinite current. So we really need to add a resistor between the input buffer and the variable resistor to limit that current to some extent. Now that we've got that, let's consider what the values of all of our components should be. We've got four things we need to specify: two resistors, one variable resistor, and a capacitor. First of all, the output resistor is the simplest. The standard output impedance in most music synthesizers is 1K, so we'll just make that resistor 1K. As far as the fixed resistor connected to the input buffer, we're going to make a couple of fairly coarse assumptions, but they'll be close enough for the purposes of this circuit. First is we will assume that the maximum change in voltage at the input from one discrete value to the next discrete value will be about 10 volts. Now, it could certainly go beyond that, but that's the assumption that we will make. Now, we'll also assume that the op amp can reliably output 10 milliamps, and so if you had a difference in voltage between the output of the op amp and the voltage stored on the capacitor of 10 volts, and you can reliably source or sink 10 milliamps, that implies that that resistor should be 1K. So that when the variable resistor is set to zero, you've got 1K between it. 10 volts divided by 1K, it gives you your maximum of 10 milliamps. Now that we've got those two fixed resistors set, let's consider what that capacitor needs to be. For the maximum slew rate, the fastest one, that means that your variable resistor will be set to zero, so your RC circuit simply consists of that 1K fixed resistor and whatever that capacitor is. We said in the previous video that we want the time constant to range from 5 milliseconds to 10 seconds. So with the variable resistor set to zero, we've got 1K there, and we want, with that, that's the fastest, so that would be your 5 millisecond time constant. This implies that that capacitor should be 5 microfarads. 5 micro times 1K is 5 milli. So there's your 5 milliseconds. Now, we've got our capacitor selected. With that, once you get up above about 1 microfarad, you typically get into electrolytics, but we really don't want an electrolytic here because the voltage on that capacitor might be positive or it might be negative, and most electrolytics are polarized, so that's not such a good idea. For non-polarized devices, whether they're mylar or ceramic or whatever, you're probably more likely to find a 4.7 microfarad value than a 5 microfarad value. So we're going to specify 4.7. That'll get us very close to our specification of a 5 millisecond time constant. For the upper range, the slowest slew rate of 10 seconds, now we've got to reconsider that variable resistor is going to be set to its maximum value, and it's going to be very large. In order to get a 10-second time constant with that roughly 5 microfarad capacitor, then that would imply that the maximum resistance there needs to be 2 megohms. if we put in a 2 megohm potentiometer there for that variable resistor, then when the potentiometer is close to its maximum value, the little 1K is really negligible, so we can just sort of ignore that. There's not a lot of difference between 2 meg and 2.001 meg. A couple of other practical issues. First of all, when you're connecting a potentiometer as a variable resistor, you can just connect one end of the potentiometer to one part of your circuit and the wiper to the other, and leave the other end of the potentiometer unconnected. However, it's generally good practice when you're doing this for the end of the potentiometer you might leave unconnected to simply connect it to the wiper. Basically what you're doing is shorting out that section between that point and the wiper. If you're wondering why this is the preferred method for doing that, please refer to the videos on potentiometers. The last thing we need to do, and this is purely a user interface issue, is we do need to pay attention to how the parameters of the circuit change relative to the direction that you turn the knob. Usually counterclockwise means less and clockwise means more. So if we turn the knob clockwise, we probably want more slew, which actually is a slower slew rate. So you could make a case for the opposite situation. But in general, you want more slew with a clockwise rotation. So the right side of that potentiometer should be the clockwise direction. The left side should be the counterclockwise direction. And whenever you're designing anything, just from a practical standpoint, you need to keep in mind which end of the potentiometer is clockwise, which is counterclockwise, and select those points so that it makes logical sense the way we expect controls to work. In our next quick video, we will listen to a couple of actual audio examples of a slew limiter.